You know, they're all around us, every single second of every day, but we can't see them. I'm talking about radio waves. Today, we're going to follow just one of those signals on its incredible, completely invisible journey to really get a handle on the complex physics it has to navigate just to get to your phone or your radio.
I mean, it seems pretty simple, doesn't it? A signal just goes from point A to point B. But what if there's a mountain in the way? Or what if you're stuck deep inside a concrete building? Somehow, the signal still gets through. How does it do that? Well, that is the fascinating mystery we are unpacking right now.
Okay, so to understand the really complex journey, we've got to start with the simplest one possible. Let's just imagine our signal is traveling through a perfect vacuum. Think deep space with absolutely nothing in its way. This is our baseline, the ideal trip.
But even in this perfect empty vacuum, there is one fundamental rule our signal just cannot escape. The farther it travels, the weaker it gets. You can think of it like shouting. Your voice gets fainter and fainter the farther away you are, right? That's because the signal's energy is spreading out over a bigger and bigger area. And this chart right here shows you exactly what that looks like. Engineers call it free space path loss. See how all those lines slope up? The farther the distance, the more the signal fades out. But notice the different colored lines? Those are for different frequencies. And look, the higher the frequency, the steeper that line gets, which means it loses power even faster. This is basically the fundamental cost of travel for any radio wave, period.
All right, let's bring our signal back down to Earth. And suddenly, things get a lot more complicated. See, the ground isn't just a platform to stand on. For a radio wave, it's this giant active player in the whole journey.
So, in most real-world cases, a receiver actually gets at least two copies of the very same signal. The first one is the direct wave, that's the straight shot, but the second is the ground-reflected wave, which takes a little detour by bouncing off the Earth. Now, these two waves can arrive out of sync with each other and interfere, which can sometimes make the signal stronger, but other times it can cancel it out almost completely.
But get this, the ground can also be a guide. At lower frequencies, a signal can literally cling to the surface of the Earth and just follow its curve. This is called a surface wave, and it works especially well over conductive stuff like seawater, which is exactly how AM radio signals can travel for hundreds of kilometers, way beyond the horizon.
So, the signal can interact with the ground. But what happens when there's something solid blocking the path? A hill, a skyscraper. You'd think the signal would just slam into it and stop dead. But oh no. Radio waves have a very clever trick up their sleeve.
They bend. It's this amazing phenomenon called diffraction. A wave can literally curve around the edge of an obstacle and fill in the shadow behind it. This is exactly why you can still get a radio signal even when you don't have a clear line of sight to the transmitter. The wave, somehow, finds a way around.
But for that bending to work right, a signal needs some breathing room. It doesn't travel as an infinitely thin line. It's actually more like an invisible, football-shaped bubble that's traveling between the transmitter and the receiver, and that space is called the Fresnel Zone.
And that bubble, it needs to stay mostly clear. The rule of thumb for engineers is to keep at least 60% of this zone free from any obstacles. If a building or even a big tree just pokes into the edge of that zone, it starts to mess with the signal. You've really got to give the wave enough elbow room to travel happily.
Okay, so far we've traveled along the ground and we've bent around buildings, but what about crossing an entire ocean? For that, our signal has to look up, way up. And honestly, this is the most dramatic part of its entire journey. So here we can see the layers of our atmosphere. We all live down here in the troposphere, where all the weather happens. But for long-distance radio, we're interested in that layer much higher up, starting around 60 kilometers, the ionosphere. The ionosphere is a truly special place. Up here, all this powerful radiation streaming from the sun energizes gas molecules, and it literally knocks electrons loose, creating this vast region of electrically charged particles. This entire layer pretty much exists only because of the sun's energy.
And that sea of charged particles? It does something absolutely incredible. For radio waves in just the right frequency range, it acts like a giant, invisible mirror, reflecting signals that hit it right back down to Earth.
And the process itself is beautifully simple. An antenna on the ground shoots a signal up into the sky. It travels up until it hits the ionosphere, which then bounces it back down, letting it land on the other side of a continent. This is called Skywave Propagation,
and it is the magic behind long-distance shortwave radio. But this sky mirror is a little picky. It only works for certain frequencies. And as this chart shows, the farther you want to send your signal, the higher the frequency you need to use to make that bounce happen. There's an upper limit for any given distance, and that's what's called the maximum usable frequency, or MUF.
Okay, let's take a breath. We've seen our signal travel through empty space, bounce off the ground, bend around buildings, and even reflect off the sky. So now, let's put it all together and see what it looks like in the real world.
So what we've really seen is that a radio wave is not limited to just one path. It has this entire toolkit for its journey. It can travel a direct line, sure, but it can also use the ground by reflecting or even clinging to it. It can bend around obstacles, and it can take the ultimate shortcut by bouncing off the atmosphere.
And here's the most amazing part. When you're standing in a city, the signal that's reaching your phone isn't taking just one of these paths. No way. It's taking hundreds, maybe thousands, all at the same time. One piece of the signal comes direct, another bounces off a skyscraper, another one diffracts over a rooftop, and they all arrive at your antenna at slightly different times. It is an incredibly complex and beautiful dance.
So the next time your GPS signal drops for just a second, or you hear a really distant station fade in on your car radio at night, you'll know why. It's all part of this invisible, epic journey. It really makes you wonder, which of these incredible paths is the signal you're using right this second taking to get to you?